जी बेटे 45 मिनट्स 50 मिनट्स लेक्चर होता है, 5 मिनट्स अटेंडेंस और we'll study for 45 minutes. Okay, so you have to stay there. You are my student now. Today you are my student. Okay, go and sit there. ECD. Today you are my student. Go and sit there. Student Hassan, we are going to study ECD. ECD इलेक्ट्रॉनिक सर्किट डिजाइन, और हम पढ़ रहे हैं स्टेट वेरिएबल फिल्टर. हम रिकैप है, आज है 16 दिसंबर और हमने पढ़ा था recap. We studied Hasni, we studied band pass filter in last lecture, and before that we studied low pass and high pass filters, low pass filters and high pass filters, and all these filters were implemented using op amps, implemented using op amps, operational amplifiers. So, or therefore they are called, है ना, therefore they are called active filters because they provide some gain. अगर सिर्फ RC नेटवर्क हो, if there is only RC network, then it's a passive filter. हंसनी डिस्टर्ब नहीं करो बेटे, don't disturb us. They are studying. Students shouldn't sit here. Students should sit there. Okay, you're a student, sit there. Don't disturb us. So today we are going to study state variable. Hasni. State variable band pass filter. Band pass filter. ठीक है, band pass filter. It's state variable band pass filter. Right. So it's the most common type of active filter. Most common type of band pass filter. It's the most common type of band pass filter used in this community. In the community of filters, this is most commonly used filter. Hasni, 5 students have joined our class. 5, only 5. There are 30 students in the class and only 5 of them have joined. Remaining 25, they are having their breakfast, they are enjoying their sleep, they are out for shopping, etc. So they are enjoying their selves. Hasni, students are enjoying their selves. Only 5 students out of 25, out of 30 students, there are only 5 students in the class. Remaining 25 students are enjoying their selves. So this state variable band pass filter is the most widely used type of band pass filter. We have one summing amplifier followed by summing amplifier. We have already studied what a summing amplifier is. It's a summing amplifier. We have 2 resistors R1 and R2 connected on the non-inverting input of the first amplifier, and this amplifier is a summing amplifier. We have already studied about summing amplifiers. Hasni, don't make noise. This is an integrator, and how can we make it an integrator if we have this capacitor in the feedback loop? Because we know that we can implement an integrator by having this capacitor in the feedback loop, integrator, and this is also followed by an integrator. So we have 3 stages for this state variable type of state variable type of band pass filter, a summing amplifier, followed by an integrator, followed by another integrator. And to make this an integrator, we must have a capacitor in the feedback loop. So we have, in fact, this is not the output. The output is this one. This is our V out. So this gives us a feedback path from, actually we have a feedback path from here back to this resistor R1. So this is a feedback path. From the output to resistor R1, we apply input here, and from the second integrator, we have this feedback path. Since we have to make it a butterworth, so we have to have some feedback resistors too, and that we should have here, R5 and R6 resistor after this first stage. So to make it a band pass filter, so to make it a butterworth filter, we have to adjust the values of R5 and R6 so that you know that these feedback resistors, they adjust the type. To make this filter a butterworth filter, we have to adjust these values R5 and R6 and we have to take these ratios R5 or R6, Hasni, R5 or R6 from a table 15.1. So let's give them some names, R1, R2, where is R3? R3 is in the feedback loop, this one. So this is R3 to make it a summing amplifier, and then it's an integrator, R4, this capacitor C1, this is C2. So the output is this one. So we have this as the band pass output. Here we have this band pass output at the output of this second stage. So a summing amplifier followed by an integrator followed by another integrator. And from the last integrator, we have a feedback loop that comes back and feeds this summing, the second input of this summing amplifier. So how does it work? And how can we find the central frequency, the damping ratio, and the summing frequency, the central frequency, the bandwidth, and the quality factor Q. Right. So before this, we must know how does this circuit perform when we have applied at the input V in a signal or frequency less than Fc. So if frequency of V in Fin is less than the critical frequency, how should the response look like? Before we go ahead and find these three scenarios, that when we have Fin less than Fc, or Fin is equal to Fc, or Fin greater than Fc, we must have an idea that what should be the shape of the response roughly. What should be the shape of the response? It should be like this. We have this Fc, this is the band pass filter, and around this Fc, we must have some bands of frequency. We must have a band of frequency for which it allows signals to pass through, and it suppresses signals having frequencies smaller than this Fc minus bandwidth by 2, and for signals with frequencies Fc plus bandwidth by 2. So this should be the central frequency and the bandwidth. So if Fin is less than Fc, we know this is an RC network, and this is also an RC network. When Fin is less than Fc, we have the signal applied here and a signal that comes back after these two integrators. It's an RC network, another RC network. If Fin is very small, this Xc is much greater than, if Hasni, what are you doing? If Fin is less than Fc, XC1 is much greater than R4. Why? Because XC1 is 1 over 2 pi FC1. If F is small, if S is small, XC1 is large. ठीक है जी? So if R4 is small, XC1 is large. If R4 is small, XC1 is large. Similarly, XC2 is much larger than R7. So XC2 is much larger than R7. So this means that if we have XC much greater than the resistor in series, the phase shift that is introduced by this capacitor is almost 90 degrees. We have studied it earlier that if XC is much greater than the resistor, series connected resistor, the phase shift it introduces is very large compared to, the phase shift is very close to 90 degrees. The max phase shift that an RC circuit can introduce, that an RC circuit can introduce a phase shift of 90 degrees at max. So if these are very large, the phase shift introduced by the phase shift is almost 90 degrees for each circuit, for each RC network. So there are two RC networks, so 90 degrees will be introduced, 90 degrees phase shift will be introduced by this first circuit, and 90 degrees phase shift will be introduced by the second circuit. So the circuit that, the signal that we get here is 180 degrees out of phase compared to V in. So if now we are adding two signals and one of them is like this, one of them is like this, and the other is 180 degrees out of phase compared to this, so this should be like this. So we should get the minimum response. We should get the minimum response because they are cancelling each other. So they cancel each other and we get the minimum response at the output. So before FC we get minimum response, and this is what we are supposed to do, because we are going to have a filter with a very sharp selective, with a very sharp band, with a filter with good selectivity. A filter with good selectivity means that FC compared to bandwidth is very large, or FC over bandwidth, the ratio FC over bandwidth is very large. Hasni, what are you doing? So what we are going to do is we are going to claim that for frequencies of signals V in that are very small or smaller compared to FC, we are going to get a poor gain at the output. A poor gain at the output because Fin is smaller than FC, the phase shift introduced by these two RC networks is very large, 90 degrees each, almost. So in total, they introduce 180 degrees phase shift, and we get the signals cancel each other, and at the output we get approximately 0 volts. Hasni, we are busy. Hasni, don't go outside.
Oh.
Hasni, it's dangerous. Come here. It can be really dangerous. You can fall off. It's very dangerous. There is no fence. Hasni, come on, come here. There is no fence. It can be very dangerous. You may fall down. Hasni, there are flies following you. Okay. And what happens when F in is approximately equal to FC? When F in is FC, we get reasonable gain because we get a phase shift of 45 degrees when we are working with critical frequency FC. We have a 45 degrees phase shift. We have studied it earlier for an RC network. We get a phase shift of 45 degrees. if these two values, this resistance R4 and Xc1 are comparable. So we get almost 45 degrees phase shift. 45 degrees phase shift introduced by this. So we get a reasonable gain because the total phase shift introduced is the total phase shift introduced by this network is by the overall network is around 90 degrees. So we get a reasonable gain, and this is what we want. So we want to get a filter with high selectivity. This means a good gain at Fc, and for frequencies below Fc and for frequencies larger than Fc, we want poor gain. We get reasonably good gain. We get a reasonably good gain. Hasni. And then for frequencies that are larger than Fc, so if Fn is greater than Fc, so what happens then? And of course, if Fn is much larger than Fc, this capacitance would be offering a capacitive reactance that is very small compared to R. So there will be no gain provided by this amplifier, because the gain is the impedance here divided by the resistance here. So this capacitive reactance divided by this is the gain. So Xc1 becomes much smaller than R4, and Xc2 becomes much smaller than R7. So if Xc1 is much smaller than R4, this would provide a minimal gain. In fact, it will block the output, because the output is a cross capacitor and it is approximately zero, because the capacitive reactance Xc is much smaller than the resistance R. So therefore, we will get a poor response. We will get a poor response even for frequencies that are very large compared to Fc. So we will get a poor gain once again. We'll get a poor gain once again, because for this network, if we are measuring output with a cross capacitor, and if we are working at very high frequency, this capacitive reactance is negligibly small, because if this is F is large, this is very small. So we get a smaller gain once again, a small gain. So we'll get a poor gain once again. So for frequencies much smaller than Fc, we get poor gain. We get reasonably good gain if Fn is equal to Fc, and we get a poor gain once again if Fn, the frequency of the input signal, is greater than Fc. So this means we are going to get a filter. We are going to get a filter with reasonably good Fc, and with reasonably small bandwidth, or good quality factor Q. So where is the eraser? The next is we are going to find something numerically. For example, what should be the quality factor? Because if we know the quality factor Q, we can compute the bandwidth. So if we know somehow, if we come to know of the Q, but first how to select the frequency FC, how to select FC. So given this filter, we'll have to find FC and of course the bandwidth to know the band it will pass through. So we need to calculate two things. Which two things? The central frequency, FC, and the bandwidth. So if we know these two things, we can implement this bandpass filter with ease and for our desired FC and desired bandwidth. So let's see how. First, you close the door. FC. So the first thing is FC. The second is bandwidth. So we have to compare two things, FC and bandwidth, because knowing FC and bandwidth, we can have this curve plotted. FC and this is the bandwidth. So in order to plot this curve or to plot this response, we must know two items, FC and bandwidth. So FC is 1 over 2 pi r C1 because this is the op-amp from which we are getting this feedback. So this will select the cutoff frequency, and here we have this output. So this R4 and this C1, they will select the frequency, the cutoff frequency for this bandpass filter. But since it's a bandpass filter, we must know its bandwidth in order to draw its characteristics or in order to draw its response. So F versus AV. So what should be the bandwidth? The bandwidth is F naught over Q. This F naught or FC that we have, FC over Q, the critical frequency divided by Q. So if we know Q, we can find out bandwidth and then we are done. So Q for this can be computed as R5, 1 over 3 times R5 over R6 plus 1. So now we are done because we have computed FC, we have computed bandwidth, and now we can draw the characteristics. So yeah, after some simple calculations, we can compute FC, the critical frequency for the state variable filter, and the bandwidth. And now we are ready to solve a small example given here on page number 783. This R1 is 10K, 10 kilo ohm. It's given to be 10 kilo ohms. This is also 10 kilo ohms. This R3 is 10 kilo ohms. And this is 0.022 microfarad. This R4 is 1K. C1, C2 is also 0.022 microfarad. R7 is 1K. And R5, 6 are also given. This is 101. This phone is connected with my laptop and I'm online. If you somehow disconnect it with my laptop, I won't be able to teach online, okay? No. So you have to stay here, you have to stay calm, and you can have your biscuits. Where are your biscuits? Don't go out, neither here nor here, okay? So this comes out to be 7.23K. 7.23 kilohertz, and bandwidth is FC over Q. We can compute Q first and then F and then bandwidth. So bandwidth is this FC over Q, and we can compute bandwidth by first computing Q. R5 over R6, R5 and R6 are given. 100K over R6 is 1K plus 1. So we got a Q 33.7 and bandwidth is 7.23K kilohertz divided by Q, 33.7. So it's a very small bandwidth divided by Q, 33.7. So it's a very small bandwidth, 215 hertz. 215 hertz. This means that the central frequency is at 7.23 kilohertz. This is 7.23 kilohertz, and the total band is 215 hertz. This band is 215 hertz. This means this is 7.23K plus half of it would be 0.107.5. 0.107 or 0.107 K, because 215 hertz is 0.2K. So it's 0.1K, and this is 7.23K minus 0.1K. So it's a very, selectivity is very large. Q is large. Q is 33.7. It's large. So Q is an indicator of selectivity. We already know this. Q is an indicator. Of selectivity. How selective is your filter? So higher Q means it's highly selective. Is an indicator of selectivity. So higher Qs are desirable because we have to pass our signal only for a certain range of frequencies, very small range of frequencies, and we have to stop the remaining complete band. So obtaining high Qs, almost Q equal to 100, is possible using this filter. And then we have biquad filter that is actually can be obtained with a small variation in this state variable filter by only readjusting these three stages. And then we are moving to the last part of this chapter 15. This is active band stop filters. Active band stop filters. That will be the last topic of the chapter, and that will be the last topic of today's lecture 2. That is active band pass filter. Band stop filters. We have already studied band pass filter, low pass filters, and active high pass filters. So now we are going to study active band stop filters. The last topic of this lecture and the last topic of this chapter. Active band stop filters. Band stop means that you have an idea of band stop filter. You already have an idea because you know that the response would be somewhat like this. The response is that this means that the response versus frequency, it will be zero only for a small frequency, only for a frequency and with a small bandwidth, and will allow signals of all other frequencies. So it allows frequency. It stops signals in a certain band only, and allows all signals to pass through. It stops signals in a certain band only and allows all other signals to pass through. So before this, we studied multiple feedback band pass filter, a type of band pass filter. In fact, that was the second type of band pass filter we studied. Multiple. Yes, that was the second type of band pass filter that we studied, that was multiple feedback, where we had multiple feedback connections from the output to the input. Multiple feedback active. We studied band pass filter previously, and today we'll study multiple feedback active band stop filter. So multiple feedback means multiple connections from the output to the input, and it will involve a resistor R3 and a resistor R4, a resistor R1, a capacitor, and we have already studied that if we have, there is one response like this, C2, R2, and this is R1, and we have a capacitor from the output to the input, C1. So now we have one low pass and one high pass filter implemented only in one op amp. This R1 C1 form a low pass filter. We already studied that in previous lectures, and R2 C2 they form a high pass filter. And we have these extra R3 and R4, and we join them together to make this input Vn. So this is actually very much like this, like the filter that we studied earlier in case of active band pass. Band pass. In the lecture in which we studied active band pass filter, we studied a filter like this, but with these small variations, we can convert it into a band stop filter. V out. So band stop filters are band stop filters. What should be the application of a band pass filter? Applications. Perhaps the most common application of a band pass filter is suppression of hum noise. Hum noise. Suppression of hum type of noise, where how do we get this noise? We get this noise at 60 hertz and 120 hertz. So at 60 hertz we get it at 60 hertz due to noise. We get it at 60 hertz due to improper shielding. If your equipment is not shielded, so it will get interference from the signals that are present outside. So due to improper shielding, we get a hum at a certain frequency. So we get a 60 hertz hum. 60 hertz common. 60 hertz hum is common, and 120 degrees hum is also common, right, Hasni? So we can have this multiple feedback active band pass filter, and we can make calculations in the same way that we did for multiple feedback active band pass filter. So now we move on to the last part of today's lecture, is state variable type band stop filter. We'll implement one such filter and we'll solve a numerical example, and that will conclude chapter number 15. So let's start. Let's start the state variable band stop filter. The last part of band pass filter we'll study today, and we'll study in this lecture, is state variable type band stop filter. State variable band stop filter is like this. We have the state variable band pass filter, BPF, fed into fed into an op amp on its inverting input, and the non-inverting input is grounded, and of course we have a feedback resistor. So it's an inverting configuration, so it is driving an op amp in its inverting configuration, and the input is applied to a state variable band pass filter, and this is the output. Hasni. So this state variable band pass filter and used to reduce hum noise. So first we have to implement a state variable band pass filter, and then the output of that filter is fed into a non-inverting input through resistors R1 and R2. Since we studied state variable band pass filter in this lecture, we studied that the filter is implemented as it's a recap of today's lecture. Summing amplifier followed by an integrator and then followed by another integrator. So this is how we implemented. We implemented this state variable type band pass filter, and while implementing this, we studied that we can tap 3 outputs from here: 1 output, 2 output, second output, and the third output. The first output is, and we studied that the second output of the second stage, the first integrator, was a band pass filter. This is BPF, band pass filter. So it's a recap from the first part of this lecture. So we have already studied state variable band pass filter, and we studied that it has 3 stages. Band pass filter has 3 stages. This state variable type band pass filter has 3 stages, and the output of the first integrator or the second stage is band pass filter. Whereas this output is high pass filter and this output is a low pass filter. So what we are going to do now is we are not connecting this band pass output to this band stop filter, but we will be connecting this low pass, this to the resistor R1 and the output of the first stage to the input of resistor R2. So this is what we are going to do now. So we'll implement this first, and this output will be given to the input of resistor R1, and this output high pass would be given to the input of resistor R2, and that will complete our state variable band pass filter. So the circuit will then contain this one amplifier, the summing amplifier, one op amp, second op amp, third op amp, and this finally this fourth op amp. So now we are going to draw a bigger circuit with 4 op amps. The first 3 will be implementing the state variable band pass filter, and if we add the fourth stage, that will become this. That will implement this band stop filter. So let's now draw the whole circuit. Hasni, I'm busy. Please don't disturb me. I'm really busy. So now we are going to draw the last circuit for today. The state variable band pass filter first, that we have already drawn. A summing amplifier first. with some feedback resistor, and then another resistor, and then an integrator. And of course, if it's an integrator, there is a capacitor in the feedback loop, then another integrator with a resistor in series and a capacitor in a feedback loop. And finally, a feedback band pass filter. So now we are using this once again to implement this state variable type band stop filter. So this is V in, this resistor is R2, R1, this is R2, this feedback resistor is R3, this is R4, this is R5, this is R6, this is R7. And this is capacitor is C1, this is C2, right? So we have once again implemented the same state variable band pass filter that we implemented in the first part of today's lecture. And then we are going to implement the second part. Resistor, we need two resistors, R1 and R2. So let's rename those because we have already used the names R1 and R2. So let's rename these resistors as what should be the names? R7, this should be R8, and this should be R9. And then we have this inverting amplifier implemented. Negative, this is positive. Oh. Actually, they are the same. Positive, this is grounded. So this is inverting amplifier. So we have two. This should come from the low pass output, and this should be connected to the high pass output of this band pass filter. And we have this feedback resistor R9 or R10. So which one is the low pass output? So anyone can be. Anyone can be connected to anyone. This is low pass output, we know, and this one is the high pass output of band pass filter. So low pass should be connected with the low pass, and high pass should be connected with the high pass output of the band pass filter. So this band pass filter followed by this inverting amplifier makes a band stop filter. Oh, so this is the last circuit, a very long circuit, but it's easy. Seriously, it's a very easy circuit. So now we are going to solve an example. The last part, the last 5 minutes, we are now in the last 5 minutes of today's lecture. We are in the last 5 minutes. We are now in the last 5 minutes of today's lecture where we're going to solve an example, and we are given these values. This value 10K, R1 is given to be 10K. I'm not writing ohms because I'm in a hurry. This is 10K, 10K, C1 is 0.22 micro. I'm not writing farad. R4 is 12K. R5 and R6 are not given, R7 is 12K, R5 isn't given, R6 is also not given, R7 is 12K, 0.22 micro, this is 10K Hasni, R9 is 10K, R10 is also 10K, right, giving a gain of -1. And given all these values, we need to find first of all the cutoff frequency F0. First of all, we need to find out F0, and then we have to find the values of R5 and R6 if you want to ensure this F0 and Q is equal to 10. So first let's calculate F0. We know F0 is 1 over 2 pi R4 C1. R4 C1 or R7 C2 you will reach the same answer. 1 over 2 pi. R4 is 12K times R7, C1 0.22 micro. So you get 60 hertz, F naught is 60 hertz. Amazingly, it's going to be a hum suppressor. It's going to be a hum suppressor. 60 degrees hum suppressor. Hum suppressor, Asni. And then we have to ensure Q is equal to 10. In the second part, we have to find the values of R5 and R6 if we want to ensure a good selectivity. We want to ensure a good selectivity. Q is equal to 10. So Q is F naught over dW, bandwidth. So Q is equal to 10. If you want to ensure Q is equal to 10, what should be the values of R5 and R6? It's easy because we know that Q is 1 over 3 times R5 over R6 plus 1. We have already studied this. So we can multiply 3 here. This becomes 3Q. This is R5 over R6 plus 1. So if we take this one here, this becomes 3Q minus 1 is R5 over R6, or it can also be written as R5 is 3 times Q minus 1 times R6. So if we select one value of R6, we are free to choose that. We can compute the value of R5. So let's choose. So now it's our choice. Now it's the matter of our choice. Let's choose. R6 to be equal to 3.3K, 3.3 kilo ohm, and put 3.3 K here. So R5 comes out to be 95.7K. So 95.7K. So this much ohms. R5 95.67 ohms, 95.7 ohms. So this will ensure 60 hertz hum suppressor or 60 hertz hum blocker at blocker state variable type band pass filter. So before we conclude this lecture, here is an assignment for you. Assignment is that you have to design. We already know that there are two hums. One is at 60 hertz, the other is at 120 hertz. Design a 120 hertz hum blocker using state variable type. Using state variable type Bandstop filter, right? And I want it to be implemented for Q is equal to 10 and for Q is equal to 20. So if you want to have higher selectivity, I want to be very selective for 120 hertz. So Q is equal to 10 and Q is equal to 20. For these two selections, you have to design two circuits and they both should stop 120 hertz hum in a circuit, in a certain environment. So you have to design two filters. They both are 120 hertz hum blockers, and one of them is for Q is equal to 10, the other is for Q is equal to 20. So that is your assignment. Right. That's all for today's lecture. That's all for today's lecture. And now we will start chapter number 16. Chapter number 16 in our next lecture, scheduled on coming Monday. Thank you.